Hello everyone and welcome to Physimania. In today's video, we're going to read scientific paper number 2. Okay, so again, as we did about 2 weeks ago, I went to the archive, I got a paper which I thought was interesting, and then we kind of like went through the paper together. We saw what it was telling us. Today, we're going to do the same thing. I found another paper very interesting with some interesting results, which I thought should be fun to learn about. And so yeah, that's the plan for today. Hope you like the video, so just let's get started. All right, so this paper is basically telling us, or let's just read the title and see what it's telling us. This paper is saying hints of new physics for the Hubble tension, violation of cosmological principle. So what this is basically telling us, okay, or what the title is trying to say us is that from the Hubble tension, okay, the Hubble tension is basically an issue that's currently going on in cosmology, where basically scientists have tried to measure the value for H naught. Okay, H naught is basically the Hubble parameter evaluated today. So this is giving us information about how the universe is accelerating, is uh, how its expansion is accelerating. Okay, and what is its rate? That's basically the information that H naught is telling us. And so this H naught value has been measured in two different ways. One is using physics from the early universe, and then another way is by using late time universe physics. So the late time universe physics is basically related with something I talked about in the other video, which is using 2-point correlation functions, 3-point correlation functions, okay, which are basically using a standard ruler from the early universe, which is known as the baryon acoustic oscillation scale, which is basically coming from a fight between pressure and gravity in the early universe, and which after some time it causes galaxies to be distributed with a specific size in the universe. Again, I'm not going to go into the many details, but this is the physics it uses. It also uses physics from the cosmic microwave background. And from that physics, it finds a value which is close to around 67 kilometers per second over megaparsec. Okay, that's the value found from the early universe physics. Then with late time universe physics, specifically with distances of supernovas, where supernovas are just stars that are exploding and have a specific luminosity that allows us to find the distance to us, then those experiments are finding about 73 kilometers per second per megaparsecs. And the difference is not that big. The problem is within the error bars, okay, because the error bars are getting smaller and smaller for both of these, for both of these probes. And what we see is basically this creating attention, right? Because one thing is telling us one thing, something, but then another thing is telling us another. And so what this paper is basically telling us right now is that they think that from this Hubble tension, they might actually have found hints of finding new physics. Okay, so basically a way of explaining this Hubble tension using new physics, and that this leads to a violation of the cosmological principle, which, if you remember, the cosmological principle, which I've said in other videos, is the fact that our universe holds some symmetries. The first symmetry is homogeneity, which means that no matter where we go in the universe, whether we're here on Earth or we go to another planet or whatever, the physics that we see should be the same. The distributions in our universe should be the same. And also the other symmetry is that it doesn't matter in which direction we look. So basically a rotational symmetry. It doesn't matter in which direction we look, our universe should look the same. So basically kind of like the same statistical distribution of galaxies, no matter where we look. And this is kind of like also what the abstract here is telling us. It's basically telling us they have used kind of like a new model, which I'll go through and basically found that there are some hints for violation of this cosmological principle. Okay, so let me just go right to it. Okay, they basically for this, what they're going to do is again try to measure what they do specifically is they measure this H naught, but using a new model, or they do it in two different ways. I think I think there's three, but I'm gonna go only over two of those. So the first way that they do it, okay, is by using something called the distance modulus, which is basically a way of finding the distance between us and these supernovas that I was talking about earlier. Now, in the regular model, this distance modulus is given by this equation, equation 2. But in this paper, what they did was basically modify um, this distance to include two new terms, this A and this B, which in fact, this A and this B actually kind of like test for the cosmological principle. It's also a way of testing for this homogeneity and isotropy of the universe. And basically what this is telling us, okay, if our universe was really respecting the cosmological principle, then this A parameter and B parameter should go to zero. That's what we should find, and then we should just recuperate. We should just be able to find our previous formula for the distance modulus from us to the supernova. Okay, that's what the data should tell us at the end. And doing so, okay, to try to test this first method, okay, what they did, the first thing they did is was basically just using the simple lambda CDM, and then they find basically the same values that they found for the supernovas, which was basically finding an H naught at about 73 kilometers per second over megaparsecs. Now, using this new method, okay, which basically, as you see, contains that A and this B parameter, what they end up finding is that they can actually find an H naught value consistent with the early universe physics that measures this same H naught. So basically at about 66.38 kilometers per second over megaparsecs. And as you can see, for example, here they have tried to depict this is specific to what they're doing. So this will be kind of like the result from using the previous distance modulus, but now this is what they found, which is very consistent with the Planck result. Planck is basically the one that gives us this result in the early universe physics, which you see, is kind of like consistent. So basically, this curve describes the probability of these parameters being true. And as you can see, this kind of like gives you that based on this new distance model, this should actually be consistent with having an H naught value of around 67 kilometers per second over megaparsecs. The second method they used to try to prove this was basically modifying this Hubble parameter, okay, basically doing a Taylor series expansion of the Hubble parameter at around zero, okay? And this basically can be expressed in terms of this equation number 5. And basically, also one thing about this specific model, which and the way they do this is that this will actually not be valid in values that are close to 1 for the redshift equal to 1, C equals to 1 or greater than 1, because this is a Taylor series expansion, which means that you have always to be less than 1, okay? But again, that's just a side note. What they do when they do this, here in the method section, we find I didn't find it. They found basically that there are also be able to reproduce a value that is going to be consistent with this H naught at about 66, 67 kilometers per second over megaparsec. Okay. And as you can see, I think here actually they have also included the A's so they have included both both the model from before for the distance models, but then also the the new the new way of parameterizing the Hubble parameter. Okay. And that's basically just the two methods that I've seen. I mean, that I've seen more important for here. So I won't discuss the last one, but just these two. That's kind of like the results. Okay. They also kind of like make up a way of um, learning how much of an error they're reducing this from, or like how much are they alleviating. I should say that, yeah. How much they are alleviating the tension between the late time physics and the early time physics. And I don't want to say this is like different physics, but I'm saying like from the results from using early physics and late time physics. So yeah, this is very short. Just wanted to give you this. Hopefully you have learned something from here. And I'm happy to take any questions in the comment section. So please let me know if you want to know more. And yeah, thank you very much for watching.